Hi, class. Welcome to the next section, chapter 13.3. Today we are going to discuss the integral test. So, um, this is the first test that we have that we're able to test for convergence directly. Right? So, in the last section, we can test for divergence, but we weren't able to test for convergence. In the last section, we had a formula for geometric series, for telescoping series for determining the sum. Um, Sometimes we can't determine what the sum is, and we only can determine convergence. So this is the first test that we have that allows us to say exactly what um, if a series is convergent or not. So let's start off with the harmonic series. So we saw the harmonic series in the last section. It's 1 over n, um, and it was kind of hand wavy, sort of claimed that the series is divergent. Okay, and it was used as an example for why you can't just look at the limit of the sequence and use that to determine whether or not you converge. You can use that to say if you diverge, but not necessarily if you converge. Okay. So consider the harmonic series. Okay, we have 1 over n. If we graph out the function, 1 over n, it's a decreasing function, right? It's basically, so this is y over x, I should say. This is the series, I'm sorry, the function y over x. And so if we remember what we talked about in the last section, where if my function is equal to my series at all of the whole number of values, then the limits of the function and the limit of the series is equal, right? And so for this, if you look at our function, if I plug in 1, I get out 1, just like I would into my sequence, right? If I plugged in 2, I get 1/2, just like I would if I plugged in 2 to my sequence. Okay, now 1 plus 1/2 obviously is not 1/2. Okay, so this isn't giving us the sum. We're just saying that the values are the same. And from the theorem that we had in the last section, we can talk about equating the limits. Okay, so if I'm looking at the series, right? The series is me having equidistant, basically rectangle representations with heights that are equal in value to my function. Okay, because for a series, I am moving, it, the height is given by the value in the sequence multiplied times 1, I can think of it as. Okay, and so here I have a rectangle of base 1 and height of my function value. Okay, so if I take this area and I add it to this area and this one and so forth, the sum of these areas are equal to the sum of my series, right? Because each value, a value of 1 over 1, for instance, is the same as 1 times 1. A value of 1/2 is the same as 1/2 times 1. So these rectangles, the sum of these rectangles is equal to the sum of my series here, 1 over n. Okay. So using a Riemann approximation, we can see that each rectangle has a base of 1 and a height of my function height, which is 1 over x. Okay. Therefore, the approximate area of 1 plus 1/2 plus 1/3 plus 1/4 and so forth and so forth, the harmonic series, is an overestimate for the integral 1 over x from 1 to infinity. It's very easy to see here that my function height and the length of the width of the base of the rectangles, um, that is indeed an overestimate of the area under 1 over x from 1 to infinity, from the same point forward. Okay. So to put this otherwise, 1 to infinity of 1 over the integral of 1 over x with respect to x is a lower bound for the sum of the series. Okay, so my series, my harmonic series, is larger than this integral, this area. So this area that I have from 1 to infinity of 1 over x, it's a lower bound. It bounds it on the low side. And I know that the area under this curve diverges from 1 to infinity from our study of um, proper integrals, right? That this diverges. So since my integral diverges and my sum is larger than a divergent area, then that means that this harmonic series is also divergent. Okay, so that's our proof for, or our demonstration there of the divergence for the harmonic series. So that brings us to the integral test. Okay, suppose that f is a continuous function that is always positive and decreasing from 1 to infinity, very similar to what we had here for 1 over x. Okay, and let my sequence be equal to a function at all the values of and all the integer values. It takes on the same value as my sequence. Okay, then the series of, so the sum of the sequences of uh, a sub n is going to be convergent if and only if the improper integral from 1 to infinity, so over that same area, same distance, I should say, of my function is also convergent. Or, to put this in simpler words again, if the integral from 1 to infinity of my function is convergent, then my series is going to be convergent. If the integral from 1 to infinity of my function is divergent, then the sum is going to be divergent as well. Okay. So again, I can't use this on every function. This integral test only works if my function is continuous, positive, and decreasing on this interval. Okay. Not only that, but it has to match up with the model of my sequences given by A sub n. Okay. So two important things that we need to take away from this. First is the P series. Okay, we study the P series when we're doing improper integrals. If you don't remember how that works, I suggest you go back and review it. We will talk about it right now, but it is important to be very familiar with it. So if I have a sum of a P series, so it looks like the harmonic series, but the denominator n is raised to the power P. Um, this P series is going to be convergent if P is larger than 1, okay, and divergent for any other value of P. Again, this was an important takeaway that we got from studying the improper integrals because we had an integration with 1 over n to the P where this holds true as well, right? The second is that the sum of the series is not equal to the area under that curve, okay? We can use this area under the curve to sort of compare what the series is doing. And so the series does the same thing that the curve does as far as convergence or divergence, but the areas are not the same. Okay. The area under this curve is not the same as the area of the sum. So we cannot, okay. So first important thing is the P series. The second is that we cannot assume that those two values are equal. In fact, they most of the time are not. So do not equate those. Okay, so let's talk about estimating the sum of the series. So again, when we talk about estimating, this is a guess. Whenever we estimate, we always use some sort of a numerical method or approximation, right? Um, so the error in a partial sum can be found by subtracting the partial sum from the actual sum, right? That's the error, what the true value versus your approximation. So our partial sum is an approximation of the real sum, right? Obviously, we're not going to add up all of the values unless it's something like a geometric series where we can figure out what it is right away. But we call this the remainder. Okay, the remainder is what we have left after we've added up a certain number of terms. Everything that we haven't added up, the sum of that is the remainder. Now that's remaining, that is our error, right? So the remaining value is a, and so if I've added up to the nth term, the n plus 1th term, plus n plus 2 term, and so forth for the remainder of infinity is the remainder. That's the error. That's the difference in what I found. Okay. So recall that each term in the remainder can be modeled with a rectangle of base 1 and a height of a sub I, whatever the value is for that a term. Okay. So the remainder is less than or equal to the integral from n to infinity of f of x. So if the remainder is an underestimate for the integral, it will look like this. Okay. So here I'm looking at n plus 1 term, and here I'm taking my rectangle to go to the left, okay, instead of to the right over the value. So this will be an undervalue. So the sum of these rectangles is going to be an underestimate, okay? It'll give a lower bounds for the area under the triangle, or curve, I should say. Now, if the remainder is larger than the integral, so here starting from n plus 1, okay, here I would be taking it to the left. And so here, I'm sorry, the right. And so the area under the curve from n plus 1 forward is then an underestimate for the sum, for the remaining values. Okay. So therefore, the integral from n plus 1 to infinity of a function is going to be bounded by the remainder, okay, which is also less than if I took the integral from n to infinity, which should make sense because from n to infinity is more, there's more under the curve than there is from n plus 1 to infinity, right? If I'm talking about the difference from n to n plus 1, starting from n, moving forward, there's more area than from n plus 1 moving forward, looking at the area, right? So the n to infinity is the larger bounds. The remainder is less than that. And from n plus 1 to infinity is the lower bound, and this remainder is somewhere between those two values. Okay, so this is the remainder estimate for the integral test, which we will see later on as well. Okay, so since the remainder is found by taking the true sum minus the partial sum, it should make sense that if I add up the first n values, the remaining of those values, if I added them all together, that would be the true sum. Okay, so the remainder plus the nth partial sum is equal in value to the sum of the series. So um, we can rewrite this as, because Rn and Sn, right? So Sn is given here. This remainder, right, we know was larger, okay, it's larger than n plus 1, but it's still less than s, right? So this gives me a lower bound here, right? This was the low bound. Oh, sorry. The remainder was larger than that. Okay. So s is definitely less than this because this value is less than Rn, right? So what I'm doing is I'm replacing the remainder with the lower bound of the estimate, which is going to be less than s because remember this value is less than or equal to Rn, right? I can do the same thing on the other side, right? Sn plus Rn is all of s, but remember this is larger than or equal to Rn, right? So then it gives me this nice little double-sided inequality, and it tells us how the sum is bounded below and bounded above, which is nice because it can give me an interval um, for a best guess for what the true sum should be. Or, if possible, if I'm looking at the limits of both of these things, that will allow me to squeeze the true sum in between those two values as well. So that's always useful. Okay. So this tells us how S is bounded below and above, and it allows us to give us the estimate for the sum. So let's do an example. So let's use the integral test to determine divergence for first n to the negative 4. And so n to the negative 4, if we rewrote this, this would be the series where all the sequences are 1 over n to the 4, which is a convergent p series where p is 4, which is larger than 1, which is what we need. Okay. Here we have 2 over 5n minus 1. Well, this is not a p series. Okay. It's sort of a shifted around harmonic series, right? Multiplied by 2, 5 in the denominator, minus 1. So it's not necessarily harmonic, but it's definitely not a p series. And so for this, we can take the integral. So we need to see, does this follow the conditions? Is this always positive? Yes, it is. Is it decreasing in value? Yes, it is, because as this gets bigger, the whole thing gets smaller. And then what were our other conditions? It has to be positive. It has to be a decreasing function on 1 to infinity and continuous on that interval as well. And if that's true, then we can look at the integral in order to talk about the series. And so, yes, we do have, okay, that is positive. We have that as decreasing. The only place it doesn't exist is at 1/5, which is less than 1. So we can take the integral from 1 to infinity and not worry about any discontinuity here. And so that's what we'll do, right? So this function is positive and decreasing on the interval from 1 to infinity, which means that I can now take the integral from 1 to infinity and talk about what it's doing. Okay, so it looks like I missed a dx right here. So I'm telling on myself. I'll fix that on the write-up before I post this, my Canvas course for my students. Okay. So, anyways, it's 1 to infinity. It's an improper integral, which means that I got to replace this with t everywhere for x. And I'm going to look at the limit as t goes to infinity once I turn this into a function, right? So I'm going to go ahead and integrate this. I could do a u sub. It's a very straightforward u sub, right? Um, so we're going to get 2/5 limit natural log 5x minus 1 evaluated from t to 1 and looking at the limit as that as t goes to infinity. And so I just plug in t here. When I plug in 1, I'll get 5 minus 1, which is 4. So that's this natural log 4 here. This is natural log 5t minus 1. And as t gets very large, I'm taking the natural log of very large values. Natural log, uh, the limit of natural log is infinity. So this goes to infinity and then minus natural log of 4. So it diverges. Okay. So therefore the series diverges as well because it does the same thing that its integral does. Let's look at another example. So let's find the partial sum for A in the last example, accurate to 3 decimal places. So we have A and B. So I'm looking at n to the -4. I know it converges. B did not converge, so it wouldn't make sense to, well, we could still find partial sums, but we want to find the partial sums for the first 1 over n to the 4th, accurate to 3 decimal places. So I need my remainder to be less than 0.001, right? The 1 in the 3rd place means that I would be accurate in that 3rd place. So this is what I need. I need to have this less than that. So that remainder, so I need to figure out how many things do I need to add up, right? I know that the remainder is less than the integral from 1 to infinity of 1 over x to the 4th. Right here, my n is starting at 1. This integral is 1 over 3 to the n cubed. So that means that I need 1 over 3 to the n cubed to be less than 0.001 because I need my remainder to be less than 0.0001. So if my remainder is less than 1 over 3 n cubed, which is equal, or I'm sorry, which is less than 0.001, the far left side, Rn, would be less than the far right side, 0.1. So what I need to do now is go ahead and solve for n. So I can multiply both sides by 3n cubed. So I have 1 is less than 0.003 n cubed. Then I can divide by that, 0.003, and then take the cubed root, and it looks like this, right? So if I divide this out, I'll have 1 over 0.003, which is the same as 3 over 1,000. And then since it's on the denominator, I can flip it, right? So hopefully you're doing a little bit of scratch work as I'm working with you, but that's a good thing about a video is you can pause it and double check and just make sure that everything is equal and that you're understanding how I'm getting from one point to the next. So solving for n should give me this when I plug it in to my calculator. It's about 6.9336. N has to be a whole number. So I never, ever, ever round down, even if I'm very close to the bottom number. I always round up if I have uh, some decimal points. So this goes to 7 for n, I should say, since n is a whole number. So n equals 7 terms. I would need to add together in order to be within 0.001 of the true sum of s. Sometimes we can manipulate things a little bit. So let's say that I go one less and I use n equals 6. Okay. So the sixth sum is 1.081123539506, yada 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 yada. So here I'm trying to stay as accurate as possible. Again, I want to be accurate to the third decimal place to this one. So I'm just including lots of decimal places afterwards so I can kind of see what's happening here, right? The integral from 1 to infinity of n to the negative 4 is going to give me, I'm sorry, from 7 to infinity. So on the next term, it's- for the remainder, would be 1 over 3n to the 7th cubed. Okay. And from 6 to infinity is 1 over 3 6 cubed. Okay. And so my lower bound, the sum at 6, and one more than n to infinity is going to be given by s6 plus the integral at 7, okay, from 1 to infinity of the function, which is around 1.082095357. Okay. The upper bound is given by Sn plus n to infinity of my function. So I know to the six terms being added together, and then this is from six up, which gives me 1.082666749. So the difference between these bounds, okay, if I subtract them, is 0.00057139139, yada yada yada. So if I choose my approximation for S to be midway between this upper and lower bounds that I have for the sum of S, then I will be halfway from this um, as far as accuracy goes. Okay, so I add these two bounds together and I take the average, and that gives me 1.082381053, which is right in the middle between these two terms. And so that is approximately equal to the sum of 1 over n to the fourth power. Okay. And it's going to be within 0.0002 of the actual sum. So when I had n equals 7, I was able to be within 0.001 accuracy. So using one less term and being crafty about it, I'm actually able to be even more accurate than I was from what I calculated for my necessary uh, number of terms that I needed. So basically what I'm doing is, right, we had this remainder theorem here that my remainder is between the n plus 1 to infinity and n to infinity. And then I replaced this form in order to find this bounds. So I found a lower bound and I found an upper bound. Halfway through that bound cuts my error in half, right? So if my bounds were uh, had more of an error than the n that I calculated for the number of terms that I needed to add up to be accurate, okay? So 1.0811 I know is not 7 terms. This is 6 terms, so this is less accurate than 0.001. I can use this bounding of using the integrals with that partial sum in order to be even more accurate than I was for um, what I needed, right? So instead of being 0.001 away, I'm 0.0002 away. Okay. So again, we're able to get within an error of 0.002 with n equals 6 instead of being within 0.001 with n equals 7. Okay, so um, that's pretty nice. Right? Okay, see you guys on the next one.